So rotational motion is different from circular motion, and the difference is that the best example is the Earth goes around the sun. That is circular motion. The Earth spinning on its own axis is rotational motion. So you clearly see the difference there. A ceiling fan, rotational motion. A stone at the end of a string, which you whirl around, is circular motion. So in rotational motion, the axis of rotation should pass through the object. That is the key. In rotational motion, the axis should pass through the object. So don't get confused between circular motion and rotational motion. And obviously, in rotational motion, you're going to talk about angles. So do you know the definition of an angle? First, what is an angle? How do you define an angle? Most people don't know that. Angle is length of the arc divided by radius. That is what has come up there. AB is the length of the arc. Theta is the angle. And theta is just AB divided by the radius. AB divided by the radius. That is the definition of angle. The actual unit of angle is radians, not degrees. So if you follow this definition, you will be getting angle in radians, not in degrees. So that's why it says angle in radians is the length of the arc divided by the radius. So theta is AB divided by R. Okay, let me ask you this. What is the angle around a point? Just because I'm recording doesn't mean that you have to be quiet. It will become so dead. What is the angle around a point? 360 degrees, isn't it? But we're not going to use degrees. So how much is it in radians? 2 pi radians. You know how we get that? What is the circumference? 2 pi times the radius. 2 pi r. And you divide that by r. The radius cancels off, and what do you have? 2 pi. So that is why the angle around a point is 2 pi. So how do you convert radians into degrees? Like I said, 360 degrees is 2 pi radians. That's a symbol for radians, a small c. So how much would 30 degrees be? All you got to do is multiply by 2 pi divided by 360. Because 2 pi radians is 360 degrees, right? So you would get it as pi by 6. Same thing, 45 degrees. Again, do the same. You will get pi by 4. 180 degrees is, of course, pi by 2. 90 degrees is, what did I say? 180 degrees is how much? Pi. And 90 degrees is pi by 2. So you need to know that. That's the basic stuff that you need to know. Rotational motion, it's a new chapter with, if you do not understand it, it has like 25 formulas in it. But at the same time, it's exactly the same formulas that you had in chapters 2 and 3. What is the difference? In chapter 2, you are talking about translatory motion, linear motion, motion in a straight line, isn't it? Now you're talking about rotation. So you're going to see the terms change. For example, instead of displacement, delta x, you're going to have delta theta. Instead of velocity, linear velocity, you're going to have angular velocity. Okay, let's, how do you define linear velocity? What's velocity? Chapter 2. That's the unit. What's the formula? Displacement over time. Okay. Isn't it clear what angular velocity is? If you're thinking, that's theta over time. For you, it's actually better to write this because it's a calculus class. Okay? So dx by dt. Okay, what is acceleration? Chapter 2, acceleration, dv by dt. Acceleration is the change in velocity divided by time. Okay, corresponding term here, angular acceleration, alpha. What would it be? See, this is so easy. D omega by dt. This is like a review. Just need to know what changes. Do you see that? Okay, now some of the equations. We had this equation to start with. V2 is V1 plus AT. Remember that? Or A delta T, whatever. Okay. And corresponding? In rotational motion? Omega 2 is omega 1 plus alpha t. Okay, you have another equation that we call the king. One half A delta t squared, right? How would that one change? Delta theta. Because delta x is, see, linear displacement is angle now, that's all. Is equal to omega 1 delta t plus 1 half alpha delta t squared. Okay, one more equation that we had was V2 squared is equal to V1 squared plus 2A delta x. Anybody remember that? How would that one change? How would that one change? That would be omega 2 squared is equal to omega 1 squared plus 2 alpha delta theta. So if you look at it that way, this chapter is not tough. It is not. If you can make the comparison, then you only have like 5 extra formulas. If you can't, then you have 25. Okay. Angular velocity. I just gave you the comparison. I'm going to look at it one by one. Angular velocity omega. I told you it's defined as the rate of change of angular displacement, isn't it? Angle described in 1 second. Again, angle described in 1 second. So theta is the angle. In t seconds, omega is theta by t. The unit, what would be the unit of angular velocity? Radians per second. That's it. So that's the unit, radians per second. Because angle is measured in radians, time is in seconds. That's how you write it, rad per second. Now we'll try to connect this with frequency. What do you mean by frequency? Number of rotations in 1 second. So if F is the rotations or revolutions in 1 second, can somebody relate it to angular velocity? If F is the frequency, what is the angular velocity? Need some thinking now. How do you get that? Most people say, what? If something makes 2 rotations in a second, 2 rotations in a second, what is the angle covered? Isn't it 4 pi? Because in each rotation, the angle covered is 2 pi. So if there are 2 rotations in a second, the total angle covered in 1 second is 4 pi. Isn't that the angular velocity? Yes, it is. What if it makes 4 rotations in 1 second? Well, then the total angle is 16 pi. No, I mean 8 pi. 8 pi. So you see a formula that comes up. Omega is 2 pi times F. Very important formula. Angular velocity is 2 pi times the frequency. So if F rotations are made in 1 second, omega is 2 pi times F. F is the frequency. It has to be in 1 second. Okay. Angular acceleration. The symbol is alpha. And is defined as d omega by dt, the rate of change of angular velocity. Unit, radians per second squared. Instead of meter per second squared, you have radians per second squared, right? Okay. This is again a comparison of translatory motion and rotational motion, which I already did, so I'll let it just run through. Linear velocity. Angular velocity. Linear velocity is in meter per second, and that one, angular, is in radians per second. Well, I used V and V naught, doesn't matter. This is a second look for you because it's important. Just absorb it, try to understand. This chapter is going to be easy. Isn't it the same thing? Just to show you that I'm not in a hurry. But do you see the correlation, the correspondence, what term is substituted for the other one? That's very important. Now, we have to find the relation between linear velocity and angular velocity. Okay. Let's say that there is a 400-meter race. You know, they run around in circles. Isn't that 400-meter race? Be with me. What do they compare there? Are they comparing the angular speed or the linear speed in a 400-meter race? Are they comparing the linear or the angular? Linear. Because if they're comparing the angular, this is what I would do. I would always run on the inner track. Always run on the inner track. And make the stupid one run on the outer track. This is what is going to happen, watch. I can't run so fast, but by the time this guy makes one full circle, if I make one circle too, you know what I'm trying to do, like, I make one circle, and this guy takes the same time to make one full circle. What can you say about our angular speeds? Both of our angular speeds are, this is where the thinking part comes in, see? We both completed a circle in the same time. Did we go through the same angle in the same time? When you make a circle, what's the total angle covered? 2 pi. So did I make 2 pi radians? Yes. Did the other guy make 2 pi radians? Yes. Did we take the same time? Sure. Do we have the same angular velocity? Correct. Yes, we have the same angular velocity. Can you see that? Because we both made 2 pi radians in the same time. So angular speeds are the same. But yet you know there's something wrong because our linear speeds are not the same. That other guy could run much faster than I could. So there's a difference between our linear speeds, but our angular speeds are the same. You see that? Really? Okay, therefore, you know that this must be the relation between the two. Why? Wasn't the other guy making a bigger radius? His circle had a bigger radius. Mine had a smaller radius. So although our angular speeds are the same, now you see that V1 is equal to omega R1 and V2 is omega R2. Is this making sense? So if R2 is greater than R1, then surely V2 is greater than V1, although omegas are the same. So this is my linear velocity, small radius. This is his linear velocity, big radius. So remember that there's always a relation between linear velocity and angular. I'm trying to derive it in 2 steps. Watch the math in it, you will understand. Angle is AB by radius. That's r theta. Velocity is AB by t. So it's r theta by t. So that's r omega. Got it. Important formula. Velocity is radius times the angular velocity. This is going to be a funny question, but try to answer it. A string, and at the end of the string you have a stone. And I'm rotating it with a constant velocity. I should say constant speed. You know why I changed? Direction change. Okay, constant speed. The magnitude of the velocity is the same. Okay, constant velocity. Magnitude-wise. My question, is there any acceleration involved? Is there an acceleration in this case? Question? It's moving at a constant speed. Does this object have any acceleration? Yes? What is it?
Yes, it's called centripetal acceleration.
Very good. Centripetal acceleration means towards the center of the circle, along the radius, involves no change in speed. Did you notice that? Okay, now what happens if I do this? I start slowly and then speed it up. There is still centripetal acceleration, but on top of that, there's also a new acceleration because the speed is now changing, isn't it? That is called the tangential acceleration. So in circular motion now we have to bring in tangential acceleration as well as centripetal. Did you understand that? Okay. So I'm trying to introduce both and you will see it. So there's tangential acceleration that we have not studied so far. So I'm bringing that. That is A tan dv by dt and wait, isn't velocity omega times r? Oh, didn't we get it? Dead people don't talk. Okay. Is linear velocity omega times r? Yes, it is. We got it. What can we do with that? What is constant there? In that equation, what is constant? You already see it. The radius is constant, so you take it out. Radius is constant, so you have r d omega by dt, a new formula. And what is d omega by dt? D omega by dt, alpha. So you got a new formula. A tan is r times alpha. Yes. Tangential acceleration is r times alpha. Now radial acceleration, which is also called centripetal acceleration. We are used to this. V squared by r. But velocity is omega times r, so I squared both. And then I get a new formula for radial acceleration. And now I'm showing you the directions of both. Obviously, tangential acceleration is along the tangent, and radial acceleration is along the radius. So you have both. Do they affect each other? Do components at right angles affect each other? No, they don't. So they don't affect each other because they are at 90 degrees. So you need to remember this. Direction of angular velocity. Wait a minute. Is angular velocity a scalar or a vector? Angular velocity omega, is it scalar or is it a vector? Surely it's a vector. All right, let's see your right hands. Up, your right hands. There's a reason why I'm saying this, because some people, they'll put their left hands up. They don't know the difference. Exactly. All right, just hold your fingers this way, and if the tip of your fingers show the rotation direction, the thumb shows you the direction of angular velocity. Finished. So if something is rotating this way, towards the tip of your fingers, can you see it? The direction of angular velocity is up. But if it's rotating the other way, the direction of angular velocity is down. Finished. Done. Such an easy thing physics is. That's what I'm drawing there. There you go. You see that? If the rotation is that way, look at the, what is that? The red arrow there, and the second one, the green ones. So that gives you the direction of angular velocity. Now, if it is speeding up, alpha has the same direction as omega. If it is slowing down, alpha is opposite to omega. You know that, isn't it? Speeding up or slowing down. Yeah. So that is bringing the vector thing. Got it? Yeah. Torque. All right, let me show you what torque is. Here. I don't want to scare the people outside. I'm trying to open the door, and it'll be done in 2 minutes. Wait a minute. Let me see whether I can switch down the back and forth. In trying to open the door, I'm applying a force. Number one, can I open the door by applying a force this way? No. Perfectly this way. Can I? No. No way. That is a parallel force. You see that? Parallel to the door. But what if I apply a perpendicular force? That's easy. You see the difference now? So you could have a parallel force. You can have a force at right angles to the door. Okay, good. If I apply a force here, it's easy to keep it open. But if I apply a force here, it becomes tougher. Now, it's real tough. Man, ooh, it's the same door. It's the same door. I can barely hold it there. This is my workout. I can barely hold it there. It's the same door. Is this a rotating object? Yes, it is. Which is the axis of rotation? The hinges. I mean, isn't this rotating? Now, how do you define torque? It is the product of the perpendicular force with the distance from the axis. The product of the perpendicular force with the distance from the axis. But you know what? Let's write it as, in the vector form. Hope somebody remembers cross product. Have you heard of cross product of two vectors? Do? Okay, fine. The symbol.
A cross B equals,
AB.
AB times
Sine theta.
sine of theta.
Okay. Now, torque is tau. The symbol is tau. Greek, tau. I'm teaching you Greek. I'm not only teaching you physics. I'm also teaching you Greek. Okay. It's a vector. Tau is the cross product of R and F. R cross F. That's not R multiplied by F. It's R cross F. And what's R cross F? RF sine theta, where theta is the angle between R and F. That make sense? Okay, go back to that door example. If I apply a parallel force, what is the angle? R is this. If I apply a parallel one, what is theta? Everybody's happy with 90. That's why they want to keep saying 90. Okay, 0. No, you said, but somebody else did not. After that, somebody else said 90. Parallel. That is R. That is F. What is the angle? 0. Perpendicular. That is R. That is F. What is the angle?
90.
Okay. Thank you. So a parallel force does not create a torque. A perpendicular force creates maximum torque. Is that clear? So what would be the formula for tau max? RF? Yeah, finished. R times F. Because theta is 90. Sine 90 is 1. There you see. If you like green figures. The whole picture, if I have resolved the force. Now wait a minute. Watch this closely, please. Where's the axis? Where is the axis in this diagram? Is this the axis? Yes. That's the axis. Where am I applying the force? Keep watching. And what direction did I apply the force? Do you see that the force now makes an angle theta with the distance, come on, from the axis? That's why the force is resolved into two components, perpendicular and parallel. What you see here is not F2, it's F parallel. That's F perpendicular. Which one do you need to consider to calculate the torque? Only this, isn't it? Only that. Okay. So, that's why the formula is R times F perpendicular, which is RF sine theta. Yeah, you could use caps or small. Don't worry about it. So, tau is R cross F. Unit, meter Newton. because R is measured in meters, isn't it? And force is measured in newtons. So put them together. You get the unit of torque. Ready? Are you getting it? Okay. Okay, let's bring in some more formulas. This is going to be a crucial turnaround in this chapter. Something extra coming in. I know. Let's revisit chapter 3, Newton's laws of motion. I think that was chapter 4, whatever. Do you remember I gave you this example, a fast-moving bus with two people standing in it? I do remember, I told you. One was, okay, one was, heavy, trying to be decent. And the other one is really skinny. And it's on the freeway, the bus is suddenly stopped. Who has a greater fall? The heavier one. The reason is because he has a bigger mass, and therefore he has a bigger inertia. So we saw that in linear motion, inertia depends on mass. Did you? Okay, now let's bring it into rotational motion. Is there inertia in rotational motion? Sure enough. Think about a ceiling fan that you switch off. Does it stop immediately? Does not. It keeps rotating for some time. That is rotational inertia. You see? There is inertia. But what does this depend on? Does it depend on mass? Well, sure, it depends on mass, but not only on mass. It also depends on the square of the distance from the axis of rotation. I'm going to bring it up slowly. It does not just depend on the mass alone. It also depends on how far away it is from the axis of rotation. So let me try to bring that up slowly, but surely. Okay. Now that diagram is very clear. That's a force applied tangentially and at a distance equal to the radius. I want to introduce this, though I've not written it there. There should be nobody who does not remember this form. Well, stands for father, mother, apple. Force is equal to mass times acceleration, isn't it? Now, can somebody give me something similar to this in rotational motion? At least one of the terms. Come on, one of the terms. One term. No, just one term. At least you know that is alpha. And your intelligence must tell you that this is tau. Because a force can only push an object in a straight line. It's a torque that makes it rotate. That give you some meaning? If anything rotates, it's not just a force. It must be the torque. Hello? A force can only move it forward, but a torque can make it rotate. Now, what's going to come in place of mass is called the rotational inertia. Introducing the new term, it's called the rotational inertia. Sometimes it's called the moment of inertia. The moment of inertia. Just want to follow this. Okay. F is m times a. That is m times r alpha because a is r times alpha. Just like, hold on, isn't velocity r times omega? Don't tell me that you never saw it. Velocity is r times omega? Okay, if you take dv by dt, what's the constant here? Radius. It doesn't change. So you have d omega by dt. What is dv by dt? A r alpha. Simple. So a is r times alpha. Do you see that I have substituted for a as r times alpha there? Now substitute it back, what would you get? Tau is mr alpha times alpha r. Are you watching carefully? Do you see it? Because f is mr times alpha. And then to find tau, you need to multiply with one more r. Therefore, what happens to that? mr squared alpha. Good. Good. Compare that with this now. Compare that with this. What do you see? Tau is mr squared alpha. Tau is I alpha. So what is I? mr squared. That's it. So rotational inertia, I told you rotational inertia does not depend just on mass. It also depends on the square of the distance from the axis of rotation. Didn't I? Okay. Just trying to tell you how we get that. We'll take this case. That might wake you up. Rotation. Isn't that rotation? It is. Do you see the axis? You do. Look at this. This is made up of so many particles, isn't it? I consider a particle of mass m1 at distance r1 from the axis. Another particle, m2 at distance r2, and so on and so forth. This is the time you should be watching. Okay? So there are so many particles at different distances. How would I find the total moment of inertia of the whole object? How can I find the total rotational inertia or moment of inertia of the whole object? Just take the summation of all the rotational inertias of each particle, isn't it? So that's what you do. You take the summation. So I'm trying to say for a rigid object, you just, let's say it has n particles, just take the summation. So sigma tau, which is the total torque, is that. Alpha is constant taken out, and mr squared is called I. So I got to you the formula now. I'm just trying to say that I is sigma mr squared. I is called rotational inertia or moment of inertia sometimes. Because there are people who like to think, I want to ask you this question. This object, look at it again, this object. What happens if I change the axis of rotation? Hello? I change the axis of rotation. Did the total mass of the object change? No. Did its rotational inertia change?
Yes.
Surely did. Which do you think is easier to rotate? An axis passing through its center or an axis at its edge? Which one is easier to rotate?
Center.
All right, that's why you look at the tires of your car. Where's the axis? Right in the center. Look at a ceiling fan. Where's the axis? Right in the center. Look at a washing machine. Where's the axis? Right in the center. There are very few cases where you have the axis off the center. What am I trying to say? I'm trying to say that the rotational inertia depends on three quantities. Number one, it depends on the total mass of the object, doesn't it? Come on. Sure. Number two, it depends on the position and the inclination of the axis too. This is not the same as this. You see that? The rotational inertia depends on the position and also on the inclination of the axis. Number three, mainly depends on the distribution of the particles about the axis. So it depends on the total mass. It depends on the position of the axis and the inclination of the axis. And also depends on how the particles are distributed about the axis. One good example would be to take a fresh look at the bicycle wheel. You know, you've been using a bicycle. Remember the first time you tried to ride it? I still do. So many years back, I had to fall many times. You know, that's philosophy right there. What happened if you just fell down and said, I'm giving up? You would never ride it. Good philosophy coming up. It only happens once in a while, so I'm going to use it. You kept trying, so finally, now you're doing it automatically. When you climb on into it, are you saying, I must put my left leg on this? No, it just comes automatically. The same thing happens in life and in physics. Practice, you get there. First, you fail. You don't get the answer. You get frustrated. You give up, stop it. You don't. You never. You get up, try again, more practice, you get there. It becomes automatic. Number two, remember when you were trying to ride the bicycle first, you would always look down right on the front wheel. Anybody remembers that? Somebody had to tell me, not there, look up, straight ahead. Great philosophy. You don't look at what's happening right now. You look at what's going to happen after 10 years, after 15 years. Anyway, come back. When you look at that bicycle wheel, you see that there are spokes, right? Spokes. Why did they have spokes there? And it looks like they wanted the entire mass to be distributed away from the axis. Do you see it? The place where the tires are. Isn't that the heavy part? Come on. So on purpose, they had spokes here to make the mass less and to concentrate the mass where? As far away as possible. Why do you think they did it? Are they trying to have maximum rotational inertia or minimum rotational inertia? What are they trying to have? Come on.
Maximum.
When you try to distribute the mass as far away, rotational inertia is m times r squared. R squared. Broke it. You see that? It depends more, not on the mass, but on what? Because it's the square of the distance. So when they try to have the spokes down there and most of the mass away, that means the radius is big, isn't it? Therefore, they're trying to have maximum rotational inertia. Now say, all right, why should we have maximum rotational inertia? Good. You're pedaling. You're on the road. You stop pedaling. Does your bicycle stop? That's because it has a high rotational inertia. Otherwise, it would have looked stupid and funny. The moment you stop, the bicycle would stop. Hey, great. Are you getting what I'm saying? Remember, what is inertia? And a moving object continues to move. So if you give it maximum rotational inertia, it's already rotating, and even if you stop, it's going to keep rotating for some time. Is anybody getting this? Well, there's a disadvantage. When you first start off, it's going to be a little tougher for you to get it to move. That's okay, because in a journey, you only start once, but you keep going. Did anybody get what I said? So look at it that way when you try to increase the moment of inertia. Okay, not done yet. Compare a disk and a ring. Come back and listen. Let's say you have a disk and a ring. You know the difference? Both have the same mass. Just imagine, both have the same mass and both have the same radius. All right? Which one will have a bigger rotational inertia? See, I said so much and I'm asking you a simple question. A disk and a ring, both, yeah, which one will have a bigger rotational inertia? Definitely the ring. All right, a solid sphere and a hollow sphere. Same, don't even have to complete the question, now you know. Correct? Very good. A man standing on a rotating platform. He didn't have anything to do on that day, so he just got up, stood on a rotating platform, hands outstretched, dumbbells in his hand, and feet stretched apart, right on the axis. Are you with me? And then what he does is, he drops the hands to his body, pulls the feet together. What did he do to his rotational inertia? Did he increase it or decrease it? Decreased it. A nice point, I'm going to make use of this. Do you know a formula like this? I have this space. And some are going like, what is P? Well, it was just the last chapter. Linear momentum. How was it defined? Okay. I don't know why the textbook had to have this as another chapter. Now we're taking a look into the next chapter. Because in the next chapter, there's only one formula. Okay, somebody give me the formula for this in rotational motion. If you can't, you are dead. At least the right side. If you can't give me the corresponding terms in rotational motion, oh my goodness, this is going to be on YouTube too, but still you're dead. Come on. Wherever mass appears, you don't see this? My goodness.
Okay, so I omega. I omega.
Wherever mass appears in linear motion, you're always going to have what? I. And in place of, why am I shouting? Okay, linear velocity. Right. And what is this called? Linear momentum. This is called angular momentum. Angular momentum is I omega. Didn't I teach you? Yeah, I did. Just compare. Teaching physics is easy. Okay, let's make it better. Do you know that linear momentum is conserved?
Yes.
In a collision, the total momentum before is equal to total momentum after. We're going to do a lab on that today. Rotational motion, angular momentum is also conserved. Angular momentum is conserved. That means I1 omega 1 is equal to I2 omega 2. I'll give you the case. Remember the man that was standing on the platform with nothing else to do, dumbbells in hand, feet spread out? Okay, be with me. The platform was rotating at omega 1. His moment of inertia was I1 of the system, was I1. All right. What did you tell me? When he drops his hands, pulls his feet together, what did you say happens to the rotational inertia? What happens to the rotational inertia? Decreases, isn't it? Somebody look at this and tell me, if I2 is less than I1, because you told me I2 is less than I1, isn't it? Rotational inertia, what should happen to omega 2? Increases. It'll speed up. Second example, have you seen people diving off the diving board in the Olympics? You know what they're trying to do? They're trying to make maximum rotations before they hit the water, isn't it? What do they do for that? First, they stand this way, and as they jump off, they try to bring their body parts as close as possible. Look at it. Are you getting it? Why are they doing that? They're trying to decrease the rotational inertia. Because when you decrease the rotational inertia, the angular velocity increases. All right, let's go to the, what do you call it? The figure skating or the ballet dancing, whatever. Have you seen the man and the lady? Okay, here it is. Well, I don't have a lady, but here, okay. As long as the lady is far away from the man, they are spinning with a small velocity. But do you see when he does this, pulls her to him, the rotation inertia decreases, and then you see them go, woo, is that? Same thing in skating or whatever, applied in life. It happens every day. Yeah. Think about it. Can we apply this to electrons moving around the nucleus? Yes, we can. Do electrons have angular momentum? Sure. They do. Do we know their angular momentus? Yes, we do. Well, tell me this. Do we know the velocity of each electron as they move? Sure we do. Do we know the radius of each orbit? Yes. We're talking about electrons. And you don't remember the K shell and the L shell and the M and the N? What do you do in chemistry? Scratch your head? I don't know. Don't you know that the first orbit has one subshell, the second has two? You call it what? S and SP and SP, DF. Ah, come on. We know the radius, we know the masses because we apply rotational dynamics into the atom. I just want to tell you that. So it's not just in the world outside. It's not just the ballet dance. So it's also inside the electron. Anything. And I did. That was written on the screen. Yeah, that is the equivalent of Newton's second law in rotational motion. So I'm just trying to bring it out again, trying to review moment of inertia. It's also called rotational inertia. Same thing. What's the unit? Isn't it m times r squared? So it'll be kilogram meter squared. That is the unit of rotational inertia. Unit is kilogram meter squared. And I think I told you I depends on three things: total mass, distribution of the mass, position and inclination of the axis. I don't have all of it here. I just said it depends on the axis, but I did tell you the whole story. All right. Do we have to cram this? No, you don't have to. But certainly you have to have an idea. For a hoop, I is mr squared. You have to know that. For a hoop. For a solid sphere, you have to know this too. Solid sphere, 2 by 3 mr squared. Solid sphere. I'm sorry, that's a hollow sphere. Solid sphere is 2 by 5. Hollow sphere is 2 by 3. Wait, tell me, which one should have a bigger moment of inertia? Solid or hollow? Hollow. Isn't this bigger than this? Yes, it is. Somebody's going to look at the 3 and the 5 and say, yeah, it's in the denominator. So certainly this is bigger. So hollow sphere 2 by 3, solid sphere 2 by 5. Okay. And the most important one, a solid cylinder or disk. Solid cylinder or disk. 1/2 mr squared. That's the most important one. 1/2 mr squared. Isn't this a calculus-based class? So let's try to derive one of this. This is my enjoyable moment. You know, because I try to use little calculus and try to get one of the formulas. Let's try to get this. Oh, look at I've got this. For a rod, it's 1 by 12 ml squared. You know, any. Shall we do this? This is a little bit easier to derive than this. Are you ready with me? We're going to use integration to get this formula for a disk. Wake up. Math becomes useful only when you are awake. That is your disk. We are trying to find its rotational inertia. You know what you have to do? You have to imagine that the disk is divided into small circular sections, which I'm trying to do. I'm trying to show you one section already. Take a look at that section. You see that? Now, that section has a radius x. Has a radius x, and its thickness is dx. You remember how in math x and dx comes up? It's only in physics you understand that, oh yeah, x is the distance, that's a radius, and dx is the change. You see? X is the radius of that, and dx is the thickness. Ready?
We're literally just going over stuff like this in Cal 2.
Very good. They're not supposed to do that. This is physics now. Right? Let the total mass be m, and the total radius is r. Hold on. What's the area of a disk? The area of a disk. What? Pi r squared. Isn't the mass actually distributed throughout the area? Is the mass distributed throughout the area? So I'm going to define a new term and say, all right, the mass in unit area is m divided by pi r squared. Okay, so the area is pi r squared. So the mass per area is m by pi r squared. Okay. Wait. Can somebody tell me the area of that section? Which is what I was about to write. But what's the area of that tiny section? Remember, its radius is x, thickness is dx. What is its area? What happens if you spread it? I mean, imagine that you cut it and straighten it. Wouldn't you have almost a rectangle? What would be the length of that rectangle? Would be the circumference, isn't it? How much? 2 pi x. And what is its width? dx. So what is its area? 2 pi x dx. Happens only if you listen. Otherwise it flies. So the area of that section is 2 pi x dx. Okay, what is the mass of that section? How do you find the mass of that section? Come on now. What is this?
Mass over area.
So all you got to do is multiply that with the total area, isn't it? Yeah, okay. So you find the mass of the section now. This is when I put the x and the dx. I think I should go ahead on a certain exam and ask you to derive something. I might do that. Yeah, that's when people will, oh yeah, I need to study this too. Okay. The mass of the section is m by pi r squared times 2 pi x dx. There's only math now. Cancel the pi's. And do you have 2m by r squared x dx? Okay. The last one or two steps. Next, since we got the mass, how do you find the moment of inertia of that section? How do you find the rotational inertia of the section? What's the formula for rotational inertia? mr squared. So you got to take its whole mass, which is this one, isn't it? The whole mass of that section. And what's its distance from the axis? What is its distance from the axis? Nobody's. The radius. What is its radius? X. So what do? You go the whole mass multiplied by x squared, isn't it? Wouldn't that change this to x cubed? X squared times, all right. So you find the moment of inertia of the section. So that'll be the whole mass multiplied by the square of the distance. Okay, which is 2m by r squared x cubed dx. Now the joy of teaching math in physics, you see the application. We're on the last step. You got the moment of inertia of that section, didn't you? How do you find the moment of inertia of the whole disk now? The whole disk is made up of sections like this, whose radius changes from 0 to r. What is the radius of the smallest section? 0. What's the smallest of the smallest? What's the radius of the biggest one? So you integrate between limits 0 to r. I mean, how can I can't go forward without teaching at least one of this. And each one of those formulas that you saw could be derived using the same process with minute differences. I wish I had the time, I would have derived all of them. I don't. And you're too happy about that, I know. Anyway, so you find the total by integrating. Integrating what? The whole expression. Limits, I forgot to put the limits here. It's limits 0 to r. Okay, maybe here. The constants are taken out, isn't it? When you integrate, the constants are taken out. And what's integral x cubed dx? X raised to 4 by 4. X raised to 4 by 4. So you put the limits, it becomes r raised to 4 by 4 because the lower limit is 0. And then you cancel the r raised to 4 and the r squared. You get mr squared, 2 and 4, 1 by 2. And we got it. Woohoo! It's only me who's happy. View of what we did, all the equations together. So stop that recording there.